Hey everyone, welcome to The Explainer. Today we're taking a really fascinating journey, tracking the incredible evolution of the car engine. I am so thrilled to guide you through this, because when you look at the engineering under the hood of a car, you're not just looking at a hunk of metal and wires, you're looking at literally centuries of human ingenuity. We're going to unpack exactly how inventors tackled some massive mechanical challenges, and in doing so, eventually transformed the way the entire world moves.
You know, it really all comes down to this one spectacular question. How exactly did we get from boiling water to silent batteries? I mean, it sounds a little like science fiction when you put it like that, but it is a very real historical relay race. Each generation of engineers was handed a baton of technology, realized its flaws, and then just sprinted toward a completely new solution.
So, let's quickly map out our timeline of innovation here. We start way back in the 1700s with the foundational steam technology. Then we leap to the late 1800s with the internal combustion pioneers. After that, we'll see diesel shake things up in the 1890s before arriving today at the electric horizon. As you'll see, every single era basically solved the massive, glaring problems of the one right before it.
All right, let's start right at the beginning of our timeline with the era of steam power.
Believe it or not, the first engines used to power vehicles didn't run on gasoline at all. They ran on steam. In the late 1700s, an inventor named James Watt made these huge improvements to steam engine efficiency. But, when people tried to put these engines into actual vehicles in the 1800s, they had a wall. While steam was an absolute breakthrough for massive factories and trains, early steam-powered vehicles were incredibly heavy, frustratingly slow, and demanded just massive amounts of water and fuel just to operate. Imagine trying to run to the grocery store, but having to load up huge tanks of water and coal just to get out of your driveway. It was utterly impractical for everyday personal travel.
So, those severe limitations of steam basically drew the perfect starting line for our next group of brilliant inventors. Let's move into the era of the internal combustion pioneers. The brilliant conceptual leap here is all about where the fire lives. See, a steam engine relies on external combustion. The fuel burns completely outside the engine to heat the water. But the internal combustion engine changes the game entirely. The fuel burns directly inside the engine cylinders. This single shift in thinking instantly made vehicles lighter, way more compact, and infinitely more viable for individual travel. They literally brought the fire inside.
And bringing that fire inside kicked off an absolute explosion of innovation in the late 1800s. Just look at this rapid-fire progression. In 1860, Etienne Lenoir builds one of the very first gas-powered engines. Fast forward a couple of decades to 1885, and Carl Benz takes that concept and builds one of the first practical gasoline automobiles. And right around that exact same time, Gottlieb Daimler and Wilhelm Maybach are pushing the limits even further, developing faster and lighter gasoline engines. These key inventors were all quickly building upon that internal combustion concept. It was a literal sprint to perfect it.
But to truly perfect internal combustion, engineers needed a highly reliable system, which brings us to the four-stroke foundation.
Enter Nikolaus Otto. In 1876, Otto introduced a level of genius structural organization to what was otherwise just a series of chaotic internal explosions. He invented what we call the Otto cycle. This four-stroke engine process became the mechanical foundation of most modern gasoline engines. Otto figured out exactly how to harness those internal explosions into a smooth, repeatable, and highly efficient cycle.
Let's break down exactly what that Otto cycle looks like, because understanding these four movements is absolutely crucial. First up, intake. This pulls the fuel and air in. Second, compression, squeezing that mixture incredibly tight. Third is power, the magic moment where combustion relies on the pressure and heat generated from burning that fuel-air mixture, violently thrusting the piston down and creating sheer forward power. And finally, exhaust, pushes the spent gases out so the whole cycle can start over again. 1, 2, 3, 4. Over and over again, thousands of times a minute. Crazy, right?
Now, this four-stroke process became the gold standard for gasoline or petrol engines, which quickly became the most common engine type worldwide. These gasoline engines utilize spark plugs to specifically ignite that compressed fuel. Because of this spark ignition system, the combustion is highly controlled, and that results in a much smoother, quieter ride. This is exactly why gasoline engines became the go-to choice for the sedans, SUVs, and sports cars sitting in our driveways right now.
But innovation certainly didn't stop with gasoline. Let's see how engineers began diversifying the engine.
Other inventors looked at this combustion concept and asked, okay, how can we change its very nature to solve different problems? Look at this comparison here. We know gasoline engines rely on spark plugs for a smooth ride.
But in the 1890s, an inventor named Rudolf Diesel took a completely different approach. He eliminated the spark plug entirely. No way, right? Instead, diesel engines use very high compression to ignite the fuel. By squeezing the air so incredibly tightly that it creates its own intense heat, the engine achieves incredible fuel efficiency and some very distinct mechanical advantages.
Because Rudolf Diesel's engine creates such immense torque, that twisting, pulling power, and is just so highly fuel efficient, it naturally found a different home than your lightweight sports car. Diesel engines became the ultimate workhorses of heavy transportation. They're the driving force behind commercial vehicles, massive trucks, and heavy SUVs. They totally solve the problem of moving massive amounts of weight efficiently.
And this next one brilliantly illustrates just how wild engineering can actually get. Instead of pistons constantly moving up and down to complete those 4 strokes, some engineers completely reimagined the shape of combustion. A rotary engine uses a spinning rotor inside a chamber. It is amazingly compact and can achieve incredibly high RPMs. You've probably heard of it being famously utilized in the Mazda RX-7. However, while it was an absolute marvel of compact design, it ultimately struggled pretty hard with fuel consumption and major emissions challenges.
Now, for the engines that did stick around, mostly those standard piston engines, engineers spent decades perfecting exactly how those cylinders were physically arranged inside the car. Let's look at modern engine layouts.
The structural diversity here is just fascinating. To maximize performance and actually fit different vehicle shapes, engineers designed several distinct layouts. You've got the inline engines, where cylinders are arranged in a straight line. The inline 4 is incredibly common in everyday cars. Then you have V engines, arranged in a V shape, like a V6, V8, or V12. These are super popular in performance and large vehicles because you can pack more cylinders into a much shorter space. And finally, the Boxer engine, featuring flat, opposing cylinders. Famous brands like Subaru and Porsche rely heavily on the Boxer layout because it keeps the car's center of gravity incredibly low to the ground, which massively improves handling.
But as we march further into the 21st century, the internal combustion engine is finally hitting its physical and environmental limits, and that is forcing the next massive leap in our timeline. Welcome to the electric evolution. Before jumping entirely to batteries, engineers created the ultimate bridge technology, the hybrid engine. A hybrid system combines a traditional gasoline engine with a modern electric motor. By intelligently switching between both systems, or sometimes using them together, these vehicles vastly improve fuel economy. The Toyota Prius and modern plug-in hybrids are the absolute perfect examples of this, seamlessly blending 2 entirely different eras of innovation into one vehicle to save fuel and reduce emissions.
But the ultimate technological shift moves us away from that 1800s foundation entirely into electric drivetrains. This is a complete paradigm shift, guys. We are talking about abandoning combustion entirely. There are 0 cylinders, no pistons, no spark plugs, and no exhaust valves. Just highly efficient electric motors powered directly by battery packs. It turns out, sometimes the best way to improve an engine is just to get rid of it entirely.
And it's pretty easy to see why companies like Tesla and traditional automakers have popularized this technology so rapidly. The immediate benefits over combustion engines are staggering. First and foremost, no gasoline is required at all. Because there are no internal explosions happening, the operation is remarkably quiet. Electric motors also deliver all their torque immediately, providing instant throw-you-back-in-your-seat acceleration. And because you've removed literally hundreds of moving mechanical parts from the equation, you benefit from significantly lower vehicle maintenance.
So where does all of this leave the current state of global engineering? Today, modern engines and drivetrains are entirely focused on efficiency and sustainability. Automakers and entire countries are investing heavily in this future. The focus right now is on squeezing even better fuel economy and lower emissions out of the remaining combustion engines through things like turbocharging and hybrid systems, while simultaneously making massive investments in alternative fuels and the full transition to electrification. The timeline is moving faster than ever before.
Which brings us to the end of our timeline and leaves us with one final, totally fascinating question to ponder. As we shift away from the 1800s internal combustion cycle and fully embrace the era of silent batteries, what incredible innovations will power the cars of the next century? Will it be solid-state batteries, hydrogen fuel cells, or something we honestly haven't even dreamed up yet? Engineering never stops evolving. Thank you so much for joining me to explore the amazing evolution of the car engine on this explainer. Keep asking questions and keep learning.